Well, polymer science is a very active and cross-disciplinary field which goes from physics and chemistry to material science and engineering. And there have been many both fundamental advances in terms of concepts like entanglements and the dynamics and rheology of polymers up to nanotechnology or maybe even pharmaceutical technology. So the good thing about such a research field is that it is vibrant and that you really can't predict where it is going to be. I'm very confident that there will be important advances of things we cannot imagine now, and that they will contribute both to fundamental concepts as well as new applications. But I mean, in order to be a little bit more specific, so in terms of polymer theory, I'm particularly excited about two areas. I mean, one thing is that, I mean, given the advances in synthesis and experimental techniques, polymer materials are getting more and more complex and sophisticated, so they often rely on a subtle balance of interactions at different time lengths and energy scales. And that is, of course, a real challenge for theory and modeling, namely to devise models for those systems that are both simple and predictive. And thereby, sort of, you can explore the fundamental concepts of the underlying physics, as well as sort of help to explore the vast parameter space and guide experimentalists. And the second aspect, which I think will become more and more important, are non-equilibrium phenomena in polymer science. So it is very well established in macroscopic engineering that processing, of course, has a tremendous effect on application properties of materials. But sort of the same concepts on the molecular level, how engineering and processing of non-equilibrium and kinetic states affect the properties, is both a great opportunity in terms of controlling properties and fabricating new materials, as well as a real challenge for a theoretical description.